The previous session, we saw the expression for a Taylor series of a given function about a point, about x equal to a. So let's see how we can generate the Taylor series for e to the power of x. Taylor series for e to the power of x about x equal to a. Now f of x equal to e to the power of x. And one thing that we have to know is that any derivative, any nth derivative of f of x is equal to e to the power of x itself for all n. That means first derivative of e to the power of x is e to the power of x. Second derivative is also itself. Third, fourth. So any nth derivative is e to the power of x itself. So f n a, nth derivative of f at a is equal to e to the power of a. Now, let's apply this Taylor series formula to this function. So e to the power of x is equal to sum as n goes from 0 to infinity of e to the power of a divided by n factorial times x minus a to the power of n. Now here e to the power of a is a constant. So instead of adding it each time to x minus a to the power of n, what we can do is multiply it to the sum. If we expand this summation, we get e to the power of x is equal to e to the power of a times starting with n equal to 0. So x minus a to the power of 0 by 0 factorial plus x minus a to the power of 1 by 1 factorial plus x minus a square by 2 factorial and so on. Now we can simplify this. X minus a to the power of 0 is 1. 0 factorial is 1. So 1 by 1 is 1. Here x minus a to the power of 1 is x minus a. 1 factorial is 1. So x minus a plus x minus a square by 2 factorial plus x minus a cube by 3 factorial and so on. So this is the Taylor series for e to the power of x about x equal to a. If instead of being centered at a, if we want it to be centered at a equal to 0, then e to the power of x is equal to e to the power of 0 times 1 plus x minus 0 plus x minus 0 square by 2 factorial and so on. And when we simplify it, we get e to the power of x equal to 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. So even if you don't remember this, if you just remember this formula for the Taylor series about x equal to a, then you will be able to very quickly derive this. To get the Taylor series for E itself, we want the Taylor series for E. Pretty straightforward. We make x equal to 1. So e to the power of 1 is E. So we substitute x with 1 throughout. We get E is equal to 1 plus 1 plus 1 by 2 factorial plus 1 by 3 factorial plus 1 by 4 factorial and so on. And since the first two terms are 1 and 1, we can add them. So E is equal to 2 plus 1 by 2 factorial plus 1 by 3 factorial and so on. What else do we need? We need to make sure that this actually fits throughout the Taylor series. If we take it to infinity, it actually matches e to the power of x. For that, we need to figure out the radius of convergence. So we have this series. We know this is the general formula for e to the power of x for Taylor series. So summation as n goes from 0 to infinity of x to the power of n by n factorial. Here we are assuming that a is equal to 0. Now here what we can do is this 1 by n factorial, we can write it as an. So our summation becomes summation or sum as n goes from 0 to infinity of an times x to the power of n, where an is equal to 1 by n factorial. Now here, since we are focusing on x about a, what we can do is we can focus only on an, because the convergence depends on how fast or slow an goes or increases or decreases. Now here we are going to use the ratio test. So for that we require an, which is 1 by n factorial. We need the next term, that is an plus 1. Now that would be equal to 1 by n plus 1 factorial. We divide these two, an plus 1 divided by an, which is equal to 1 by n plus 1 factorial divided by 1 by n factorial, which is equal to 1 by n plus 1 factorial times the reciprocal, n factorial by 1. Now, n plus 1 factorial can be written as n plus 1 times n factorial. And n factorial cancel. So we are left with 1 by n plus 1. So now we take the limit as n goes to infinity. What is the absolute value of an plus 1 by an, which is equal to limit as n goes to infinity of 1 by n plus 1. And as n goes to infinity, 1 by n plus 1 goes to infinity. So that means since the radius of convergence is infinity, the Taylor series converges to the function e to the power of x as n goes to infinity. That means this is exactly equal to e to the power of x if we take it to infinity. So the interval of convergence is minus infinity to plus infinity. Now here, remember, we are ignoring the x term when we are doing ratio test. Since a to an determines the convergence about a specific value of x. So that is the Taylor series for e to the power of x. Now in the next session, we will look at the Taylor series for natural log of x. That's it for now. Bye.